How do we balance chemical equations? So here's a series of steps. And as it often works with a series of instructions, they don't make a lot of sense when you just read through them. It makes more sense when you apply them. So we'll read through these, and then we'll do several examples to illustrate what these are talking about. The first step is to write a skeletal equation using the correct chemical formulas for the reactants and products. Figure out what are the reactants, what are their chemical formulas, write that down. Figure out what are my products, what are their chemical formulas, and write them down. It's really important that your chemical formulas be correct. If your chemical formulas are wrong, then the whole thing's going to be wrong. So you may need to review Chapter 5 for some nomenclature rules. The next part, this is a technique we call balancing by inspection, which means we look at it and try to figure it out. So these are guidelines. If an element occurs in only one compound on both sides of the equation, that might be a good one to start with. If there's more than one of those, try balancing metals before nonmetals. That's a guideline. You don't have to follow that. If you have an element that occurs as a free element, either in the reactants or products, probably save that one for last. And then you balance those by adjusting the coefficient. You don't mess around with the subscripts. You might end up with fractions for coefficients. If you do that, then you need to convert those into whole numbers by multiplying the whole equation by the appropriate factor. That use of fractions can be avoided if you don't like fractions. And the last step is really important. Always check to make sure that it's balanced. Go back and look at it and make sure that it's all adding up right. So these are really important. Do change the coefficients. Do not change the subscripts. Don't change the subscripts. Okay, let's do an example. Write a balanced equation for the reaction between solid chromium-3 oxide and solid carbon to produce solid chromium and carbon dioxide gas. They want us to include the state symbols because they're telling us the state. A lot of these things I would not expect you to know whether it's a solid, liquid, or a gas. A temperature is not specified. If no temperature is specified, we assume that it's at room temperature. The first thing is we need chemical formulas for the reactants and products. And so this is going to be a review of Chapter 5. So the first one is chromium-3 oxide. Well, that's an ionic compound between a metal and a nonmetal. We need to write the formula for the ion, chromium-3. That Roman numeral 3 tells us it has a 3+ charge. Oxide is from the element oxygen, and we can tell from its position on the periodic table that it has a 2- charge. And then we can do the crisscross thing and come up with the formula for the compound, which is Cr2O3. In parentheses, I'm going to put S for solid, because it told me in the instructions that it was a solid. If you're still not real confident in nomenclature, you need to work on that. Okay, this chapter is going to be real tough if you can't write formulas for compounds. Plus, what's our other one? Solid carbon. Well, carbon's an element. It says solid. Whenever we have an element, we have to ask ourselves, is it one of the 7 diatomic elements? Horses need oats for clear brown eyes. Clear is Cl, that stands for chlorine. Carbon is not one of them, so then its formula is just the element symbol. To produce, that's where the arrow goes. Yes, question? So if it was, say it was chlorine, then we need to write the formula as Cl2. So all of those would be H2, F2, N2, etc. Just those 7. Sulfur and phosphorus also form polyatomic molecules, but we're not going to worry about that in Chem 3A. We'll save that for 1A. to produce, that's our arrow, solid chromium. Okay, so chromium is Cr, solid. Is it one of the 7 diatomic elements? No, it's a metal. And carbon dioxide gas. Okay, that's a molecular compound between 2 nonmetals. Carbon, there's no prefix, and so we understand that there's just one. Dioxide means 2 oxygens, and they tell us that it's a gas. That's our starting point. Sometimes they'll give you the starting point, this skeletal equation. Other times they'll torture you. That's what it feels like. They'll torture you and make you come up with the formulas. So here's just a tip for doing problems on mastering chemistry. If they give you a question like that on mastering chemistry, try to come up with the formula yourself. But then check the formulas before you balance it and submit your answer. That's not cheating. That's checking your work. Now, obviously, you can't do that on an exam, but doing homework, you're still learning. Hopefully, you'll have it figured out by the time we take the exam. But check your work, because you're going to go through a lot of trouble balancing an equation with incorrect formulas and get the answer wrong. Now we have to look at these. Here we have carbon and chromium sitting there by themselves. We probably want to leave them for last. So oxygen, we're going to take on first. So here I have 3 oxygens, and over here I have 2 oxygens. What can I do? Yeah, I can use coefficients of 2 and 3. I could make there be 6 on each side. You could do fractions too, but my experience is Chem 3A students don't like that method, so I'm not even going to go there. If we multiply this whole thing, come on, Pointer. Come on. It's being lazy, apparently. If I multiply that by 2, now I have 6 oxygens. Yes. So if I multiply that by 2, 2 times 3 is 6. And then over here, to get 6 oxygens on this side, I'm going to put a 3. So you may be going, whoa, what on earth are you doing? Okay, think of this as a tricycle, right? A tricycle has 3 wheels. Think of this as a bicycle. How many wheels does a bicycle have? 2. So we have tricycles on one side, bicycles on the other. How many of each do we need to have the same number of wheels on each side? Can you think about that one? If you have 2 tricycles and 3 bicycles, then you'll have 6 wheels on each side. Should I draw pictures? Yes or no? Yeah. Yeah, okay. This is going to be really bad. So over here, so there's the tricycle. 3 wheels, right? 1, 2, 3. And over here is my bicycle. I don't know. It's pretty sad, huh? Stick figure bicycles. I want the same number of wheels on each side. This is kind of like what we did with balancing or forming ionic compounds. So if I put another bicycle here, I should really practice drawing bicycles. Now I've got 4 wheels on this side and 3 wheels on this side. Well, I could put another tricycle over here. That tricycle looks kind of, I don't know, there's something missing on that tricycle. But it isn't the wheels. It's got the wheels. So there's another tricycle. I've got 6 wheels over here. But I've only got 4 wheels on this side. So I need another bicycle. So if I have 2 tricycles, come on, Pointer. Oh, it didn't even finish. Didn't finish drawing my bicycle. What's up with you? Now it's working. 3 tricycles, 6 wheels. 3, did I say that? 3 bicycles, 6 wheels. 2 tricycles, 6 wheels. That's all we're doing when we're balancing equations. We're trying to come up with the same number of pieces on both sides of the equation, both sides of the arrow. Oh, that's just way too skinny. There we go. So our oxygens are fine then. Now, pick one, chromium or copper. I'm going to go with chromium because it's first over here. How many chromium atoms does this indicate? 4. And over here I only have 1. So if I put a 4 in front of it, now I've got 4 chromium atoms on that side. So chromium's balanced, oxygen is balanced. Now we need to look at the carbons. Here I have 1 carbon, here I have 3 carbons. So I need to put a 3 over here. You can start with different elements. Sometimes you might start with an element and realize, this is not going very well. Start over with something else. Okay? You can't always predict what's going to be a good one to start with. But any questions about that equation?
So that's how it's going to be written?
Mm-hmm. Let's do another one. Write a balanced equation for the combustion reaction of gaseous C4H10 and gaseous oxygen to form gaseous carbon dioxide and gaseous water. Well, the first reactant is given to us, C4H10. And I'm going to write G in parentheses because it told me it was a gas. What is it reacting with? Oxygen gas. Is oxygen a diatomic molecule, a diatomic element? Yeah, it is. So I need to write O2. This is where knowing your 7 diatomic elements becomes very important. And that's a gas. And notice I'm leaving a little space here in case I need to write a coefficient in there. Then we've got carbon dioxide. We already figured that one out. CO2. Again, it's a gas. My other product is water. What's the formula for water? H2O. And this is a gas. If it bothers you that that's a gas instead of a liquid, here we're burning something. We're burning propane. Gives off a lot of heat. It's going to be hot. The water's going to be in the gas state. Okay, so what do you want to start with? You want to start with oxygen? I don't recommend that. The reason is oxygen's all by itself. Let's leave him alone. Let's pick between hydrogen and carbon. Hydrogen, okay. So we have 10 hydrogens on the left side. There aren't any in here. And how many hydrogens do we have on the right side? 2. H2. So I need to multiply this by what? By 5 to get 10. So now I've got 10 hydrogens on each side. It's just like really weird math. It's just small numbers multiplying. There's no decimals or anything or square roots, but it's just strange. Okay, so we did the hydrogens. How about the carbons? How many carbons on the left side of the equation? 4, because there's none in the O2. And on the right side, there's no carbons over here. There's 1 carbon in here. So we need to multiply that by 4, and now we've got 4 carbons. So we've got the number of carbons and hydrogens are equal, the same on both sides. Now we're going to look at the oxygen. The oxygen is by itself on this side, but it's in 2 places over here. So let's look at this. 4 times 2 There's 8 oxygens in that one. And 5 times 1, there's 5 oxygens over here. 8 plus 5 equals 13. So I need to multiply O2 by some number to get 13. So here we've got, this is coming in pairs, right? You can't, not with a whole number. This is what I call the odd-even problem. You can use a fraction to take care of this, but most people don't want to do that. So the solution to the odd-even problem is double everything. Because what happens when you double an odd number? It turns into an even number, problem gone. So what we're going to do is we're going to double everything. So I have one of these. So I'm going to double it, and that's going to give me 2. This oxygen, this is the part I'm working on. So I'm going to leave that alone. But over here, I'm going to double the 4 to get 8, and I'm going to double the 5 to get 10. Did that mess up the balance of carbons and hydrogens? No. It doubled both sides. I have 8 carbons here and 8 carbons there. I have 2 times 10 is 20 hydrogens, and I have 10 times 2, 20 hydrogens. Now let's look at the oxygens. Here we've got 2 times 8, 16. 16 oxygens here, and 10 there, and that is 26. Ha! Even number. What do I multiply 2 by to get 26? 13. And there's my balanced chemical equation. Question? I could have used 6.5. So if I had used 6.5 or 13 halves to multiply, I could have balanced it that way. But then this is not, oops, pointing in the wrong place. This isn't a whole number, this isn't a whole number. And so then when you're all done, you're going to multiply the whole thing by 2 so that everything's whole numbers. So what we're trying to get for our coefficients is whole numbers in the lowest possible ratio. 2 to 13 to 8 to 10 cannot be reduced into a smaller ratio. And they're all whole numbers, so we're good. Any other questions? If you want to use fractions like 13 halves or 6.5, you go right ahead. I'm just not going to teach it in front of the class. Let's do another one. Write a balanced equation for the reaction of aqueous lead-2 acetate with aqueous potassium iodide to form solid lead-2 iodide and aqueous potassium acetate. That's just a whole lot of words, isn't it? Well, let's break it down. Here we've got a reactant, lead-2 acetate. We need to write the formulas for the individual ions. The Roman numeral tells us that's Pb2+. Acetate, we're supposed to memorize. C2H3O2 with a -1 charge. To put these together into a formula for a compound, we look at the charges. This is 2 and that's 1. They're not the same, so we can do that crisscross thing. And we're going to end up with Pb C2H3O2 in parentheses with a 2 on the outside. What state symbol should I write here? AQ for aqueous. And then that is reacting with potassium iodide. Well, potassium is K+, iodide is I-. +1, -1, if I just shove them together, they'll have a 0 charge. So that's Ki, and again, that one's aqueous. To form, that's my arrow. Solid lead-2 iodide. So I've got lead-2 with iodide. That's going to be Pb I2 and we're told that's a solid. And the other thing that's formed is potassium acetate. So we're putting K plus with C2H3O minus, plus 1, minus 1, K, C2H3O2, ran out of space. I'll put him down there, AQ. So that's all chapter 5 stuff. Now we need to balance this equation. Well, a lot of times I just start with the first thing. The first thing here is PB. In this formula, how many PBs do I have? Just one. I have 2 acetates, but this 2 applies only to what's in the parentheses. I have 1 PB. And over here, I have 1 PB, 1 lead. Balance. This guy looks like a mess. I'm going to skip him, come back. K. How many Ks do I have? 1. And over here, 1. Oh, cool. Occasionally you get an equation that has no subscripts, and it kind of fakes you out because you're like, it can't be that easy. Sometimes it is, not very often. So I still want to skip the acetate. How many I's do I have here? 1. And how many here? 2. I have to do something about that. So I need to put a 2 in front of Ki. That fixes the I, but it messes up the K. We need to go back and revisit K. So now I have 2 Ks over here and only 1 over there. So I'm going to have to put a 2 coefficient over there. Did that change anything that I've already fixed? Did it mess up the PB or the I? No. So I've got K, I, and PB taken care of. Now I just have to worry about this mess. This is a polyatomic ion, C2H3O2, and look, it's over here as well. It did not come apart during this chemical reaction. It just switched partners. So I can balance polyatomic ions as units if I want to. So let's do that first, and then I'll talk about the other way. So how many acetate ions are in this formula? 2. And over here, with 2 of this, how many acetate ions do I have? 2. It's balanced. Yay! What if you don't like the idea of looking at that as a whole? Well, you can look at it as individual elements too. So let's look at carbon, hydrogen, and oxygen separately. How many carbons are in this formula? 4. And over here, I have 2 of these. There's 2 in each, so I have 4 carbons there. Here I have 3 hydrogens inside the parentheses, the 2 on the outside. So that's 6 hydrogens. Over here, I have 2 of these units. Each unit has 3 hydrogens. That's 6 also. Here I have oxygen, O2, inside the parentheses, and there's 2 of them. How many oxygens is that? 4. Over here, I have O2, and I have 2 of those. That's also 4. So you can do it either way. It's a matter of preference. Any questions? Let's do this one. Here they gave us the skeleton. That makes it so much easier. Well, we probably want to leave oxygen for the end just because oxygen's by itself. Chlorine's also by itself, so it would be good to leave that to the end. The reason it's nice to leave those until the end is because if I change this, it doesn't mess up anything else. It only affects chlorine. Whereas if I change the coefficient on H2O, it changes hydrogen and oxygen. So let's start with hydrogen since he's first. How many hydrogens in HCl? 1. And how many hydrogens in H2O? 2. How do I fix that? I'll make there be 2 of these guys. Now I have 2 hydrogens on the left, 2 hydrogens on the right. Well, now I have to do chlorine or oxygen. Here's chlorine. How many chlorines do I have over here now?
1, 2.
2, because I have 2 of these units. So I've got 2 chlorines, and over here I've got 2 chlorines. Awesome. Now I'm going to deal with the oxygen. Here I have 2 oxygens, and here I have 1 oxygen. Well, I can put a 2 here. And that fixes the oxygens, but it changes the hydrogens, right? So I need to go back and fix the hydrogens. So what do I need to do? I need to change this 2 into a 4, right? So I have 4 hydrogens to match this 4 hydrogens. So I've got hydrogen straightened out, I've got oxygen straightened out. Let's take care of the chlorine. How many chlorines are in this? 4. And how many do I have over here? 2. Well, that's not so bad. I'll just put a 2 in front of that, and now I've got 4 on each side. Any questions? This takes some practice. You know, it's not calculus or anything, but it's new and different, and it's got details in it, and it just takes a little practice. And once you practice it a little bit, it becomes quite easy.